Okay, now we're going to look at a few more graphs, some a little more complicated now. So this first graph we're going to look at is f of xy, which again is just a fancy name for z, equals x squared plus y squared. Now for a graph like this, one technique we're going to use to identify what the whole three-dimensional graph looks like is the idea of traces, which I introduced in the last video with the sphere. So what I usually do if I don't know what a graph looks like is I choose some planes and I automatically choose the x, y, y, z, x, z planes when z equals 0, x equals 0, and y equals 0. And then as you can see, I'll usually do a couple more traces in one or two more planes depending on what I see in these three traces. All right, so starting with the xy plane where z equals 0, I get 0 equals x squared plus y squared, which has the form of a circle. In this particular one, the radius of the circle would be 0. But more importantly, what I learned from this is that if z was some other number besides 0, like 1 or 2 or 3, I would actually get a circle with a non-zero radius. And that's kind of important. We'll come back to that. In the yz plane, when x is 0, I get z equals y squared, which is a parabola on the yz axes. And then when in the xz plane, when y is equal to 0, I get z equals x squared. So let's see how that looks on the three-dimensional axes. Okay, so I've got x, y, z. Now, this isn't very useful. We'll talk about that, but let's talk about this one. Z equals y squared. Notice that parabola is on the yz axis, and here's the yz axis. So that is this parabola right here. That's z equals y squared. Okay. Z equals x squared is a parabola on the xz plane, which is this one right here, coming in and out of the paper. You can imagine getting that by taking z equals y squared and just rotating that 90 degrees. And that would give you the z equals x squared. Okay, coming back to the circle, when z equals 0, that's a circle with a radius of 0, which is just a point. And you could interpret that when z equals 0, you're on the xy plane, you're down here, and that's just this point, the bottom of the shape. Circles are good in the world of three-dimensional graphing because they're easy to visualize and sketch. So now that I got to know that I'm going to get a circle with different z values, I did a couple more traces for z equals 1 and z equals 2. And I got circles, and notice the radius of the circle is getting bigger. Plotting that on the three-dimensional axes, here's z equals 1, and so that circle is going to join together those parabolas. And if I move up to z equals 2, I'm getting a bigger circle, which is going to join up the parabolas as well. And you see this overall shape looks like a parabola. In fact, this particular shape we've seen before. In 17b, we did those examples where you took part of a parabola and revolved it around the axis. That's literally what this shape would be, and we call this shape a paraboloid. And paraboloids, this is probably not the last one you'll see. They're fairly common shapes to work with in three-dimensional calculus. Okay, and let's look at another one. This one we are going to definitely see more of. We'll talk about why. Maybe I'll hide the graph for the moment. So now we're looking at z equals y squared minus x squared. Once again, I'm going to do my traces in my three planes, z equals 0, x equals 0, y equals 0. Let's start with z equals 0. I get 0 equals y squared minus x squared. That's really just going to be two lines if you move the x squared over and take the square root. But more importantly, what form does this have? If z was not 0, if z was a number like 1 or negative 1, you may recognize that that is a graph that would look like a hyperbola. Hyperbolas are the graphs that have two parts to them. Okay. Not an easy graph to sketch. Hyperbolas are not super friendly to graph. So let's move on to x equals 0. That gives me z equals y squared. We had that graph on our paraboloid, the one before. And then when y is 0, we're getting z equals negative x squared. Let's see how those graphs look on my overall shape here. So the z equals y squared is this parabola again. Z equals negative x squared, if you can imagine rotating this parabola 90 degrees and then flipping it, right? It's an upside down parabola. That is this parabola right here. That's z equals negative x squared. Okay. Now, to do a couple more traces, what I decided to do was to move in the y direction, because it's really hard to do traces coming out in the x direction. That's not so easy to graph. So we moved in the y direction. This is the y-axis. And if I let y be 1, plus or minus 1, or plus or minus 2, and again, how I'm getting these equations is I'm literally just putting these values in for y. I get z equals 1 minus x squared. And when y equals plus or minus 2, I'm getting z equals 4 minus x squared. You should recognize those parabolas are the same as this parabola, just shifted up, right? This is going to be shifted up 1. This would be shifted up 4. On my graph, you can interpret that right here. Here's y equals 1 and y equals negative 1. And notice my parabolas are, I kind of like to think of them as they're hanging over the z equals y squared. Okay, they're wrapping themselves over that. And then if I go to y equals 2, and maybe this is negative 2 here, you see that the parabola moves up, right? It's this parabola here, and this one there. If you put all those together, you can start to see a shape. I kind of join those parabolas here. And this particular shape is called a saddle. Just like a saddle that you would put on a horse's back, kind of has that shape there. And we're going to find out more. We're going to hear this word saddle a lot. It's kind of a unique point. We'll talk about that later. But when you see us, when you hear the word saddle, that's the shape I want you to think about. Okay. Now, traces can be two-dimensional cuts, if you will, for a three-dimensional graph. But when we do a trace for a specific z value, we actually call those level curves. That's a common term you'll hear in this section of the book. So if you take that saddle, and you can imagine these cutting that saddle at different z values. If I cut through it at z equals 1, if I slice through it, do you see those are actually going to be hyperbolas, right? That's a hyperbola. And notice it's, okay, the reason I call them level, it's kind of flat, right? On our paper, it's nice and level, it's horizontal. When z equals 2, you're getting another hyperbola here. And if you go down in the negative z value, your hyperbola is actually changing direction. It's wrapping in and out of the paper, and then there's another one behind it. Now, if you take all of these level curves and plot them, imagine they all just fell down onto the xy plane. You can visualize, this is called a contour plot, when you take a bunch of level curves and plot them just on the xy axis. Another way I like to visualize this, imagine if you were looking up above in an airplane, you were looking down at this, you wouldn't necessarily know how high all of these lines are. You would just see a graph like this if you were looking from above. And so this is called a contour plot. So there's your hyperbolas when a equals 1. Oh, by the way, when we do a level curve, a lot of times, you know how f of x, y, we've been calling that z, but they'll also sometimes substitute, our book uses k. K just means a specific z value. So when z equals 1, notice this hyperbola is curving around the y-axis. So when k equals 1, I have, that's this hyperbola here, and it's also down below there. K equals 2, which is z equals 2, would be a further up on the y-axis. If you can imagine this would be a little further, right? The bottom of that would start further up the y-axis than this one here. For your negative z values, those hyperbolas are wrapping around the x-axis, right? They're curving around towards the x-axis. So that would be these hyperbolas. This contour plot might look familiar if you've ever seen a topological map, which is a map where they give you elevations of the terrain. If you're going hiking in a mountainous region, oftentimes you'll see a map with contour plots where they're literally giving you elevations. That's what the way you can think of these z values and k values, those are elevations, right? Those are heights. So, all right. Here I'm just showing, okay, again, you let z equal k be a random z value. And if you set k equal to y squared minus x squared, you would then recognize that all of these level curves are going to be hyperbolas. Now you can do a contour plot for all kinds of shapes. If I look at a graph like this is actually just the graph of a plane, z equals 6 minus 2x minus 3y. We actually graphed that in our first video. I just rewrote the equation and solved for z. And if I wanted to know what the level curves look like there, I would set my z equal to k. And if I solve it for x and y, move the 2x and the 3y over to this side, subtract the k, these are all just going to be lines. And if you pick different values for k, for example, if k is 0, you're just going to get 2x plus 3y equals 6, which is a line. And that, back on my three-dimensional graph, that would be this line right here. It has an x-intercept of 3, a y-intercept of 2. So that's this line. If I let k be 2, I get 2x plus 3y equals 4. That would be this line, which on my three-dimensional graph is really this one. Here's the one for z equals 4. And even when, yeah, I'm not looking at the whole plane here. This thing goes on forever, this plane. But you're just going to see a bunch of lines as your contours. A couple more examples. Here is the next one. This is the equation of a cone. Z equals the square root of x squared plus y squared. If you did the full, looking at traces in different planes like we did on the first two examples, you would see that this is just going to give you a cone. And now that I know the three-dimensional graph, if you imagine slicing at different z values, you can see you're going to get a bunch of circles. If I didn't have that graph, you could figure out that they're circles by letting, again, z be k. If I square both sides, I can tell that all my level curves are going to have the form of a circle, right? If you give me a value for k, I plug it in here, that's going to give me a circle. So I could plot some of these circles. When k equals 1, I'm going to get a circle with a radius of 1. When k equals 2, I'm getting a circle with a radius of 2, a radius of 3. So my contour plot would look like a bunch of concentric circles. And notice that these circles are equally spaced. For consecutive values of z, they're increasing by 1 unit, right? The radius of the circle is getting bigger. If I go back to that paraboloid that we graphed in our first example, it also has level curves that are circles at different z values, and you can confirm that by letting f of x, y be k. You're going to get circles as well. But notice here, the radius of your circle is, remember the radius of a circle is the square root of this number. The radius is going to be the square root of k. So what that means is your level curves, they're still going to be circles. When k is 1, you're going to get a circle with radius 1. But when k is 2, your radius is going to be the square root of 2. It's like 1.4. When k is 3, your radius will be the square root of 3, which is still not 2. It's 1 point whatever, 1.7 or 1.8. So notice one difference between the contour plot for this paraboloid is you're getting a bunch of circles that are concentric, but they're not equally spaced. Right? The radius of your circle, the distance between each circle is going to get smaller as you move, as you choose bigger and bigger k values. And you can tell that from the graph. You can see because the parabola is curving upward, as you move up one value of z, the radius of your circle does get bigger, but not by the same amount, right? It's getting bigger by a smaller amount each time. So one of the problems in our book involves this example of looking at the difference between a paraboloid and a cone in terms of recognizing it by their contour plots, right? A paraboloid, both of them are going to have circular contour plots, but you can see the difference on a cone. The circles are equally spaced for consecutive values of z, whereas on the paraboloid, they're going to be unequally spaced. All right, that's all for this video.